right triangles, laws of sines and cosines. Although right triangles allow us to solve many applications, it is more common to find scenarios where the triangle we are interested in does not have a right triangle. Two radar stations located 20 miles apart both detect a UFO located between them. The angle of elevation measured by the first station is 35 degrees. The angle of elevation measured by the second station is 15 degrees. What is the altitude of the UFO? We see that the triangle formed by the UFO and the two stations is not a right triangle. Of course, in any triangle, we could draw an altitude, a perpendicular line from one vertex to the opposite side, forming two right triangles, but it would be nice to have methods for working directly with non-right triangles. In this section, we will expand upon the right triangle trigonometry we learned in Chapter 5 and adapt it to non-right triangles. Law of sines. Given an arbitrary non-right triangle, we can drop an altitude which we temporarily label h to create two right triangles. Using the right triangle relationships, sine of alpha equals h divided by b and sine of beta equals h divided by a. Solving both equations for h, we get b sine of alpha equals h and a sine of beta equals h. Since the h is the same in both equations, we establish b sine of alpha equals a sine of beta. Dividing both sides by ab, we conclude that sine of alpha divided by a equals sine of beta divided by b. Had we drawn the altitude to be perpendicular to side b or a, we could similarly establish sine of alpha divided by a equals sine of gamma divided by c, and sine of beta divided by b equals sine of gamma divided by c. Collectively, these relationships are called the law of sines. Law of sines. Given a triangle with angles and sides opposite labeled as shown, the ratio of sine of angle to length of the opposite side will always be equal, or symbolically, sine of alpha divided by a equals sine of beta divided by b equals sine of gamma divided by c. For clarity, we call side A the corresponding side of angle alpha. Similarly, we call angle alpha the corresponding angle of side A. Likewise for side B, an angle beta, and for side C, an angle gamma. When we use the law of sines, we use any pair of ratios as an equation. In the most straightforward case, we know two angles and one of the corresponding sides. Example 1. In the triangle shown here, solve for the unknown sides and angle. Solving for the unknown angle is relatively easy since the three angles must add to 180 degrees. From this, we can determine that gamma equals 180 degrees minus 50 degrees minus 30 degrees equals 100. To find an unknown side, we need to know the corresponding angle, and we also need another known ratio. Since we know the angle 50 degrees and its corresponding side, we can use this for one of the two ratios. To look for side B, we would use its corresponding angle 30 degrees. Sine of 50 degrees divided by 10 equals sine of 30 degrees divided by b. Multiply both sides by b. B sine of 50 degrees divided by 10 equals sine of 30 degrees. Divide or multiply by the reciprocal to solve for b. B equals sine of 30 degrees multiplied by 10 divided by sine of 50 degrees is approximately 6.527. Similarly, to solve for side C, we set up the equation sine of 50 degrees divided by 10 equals sine of 100 degrees divided by C. C equals sine of 100 degrees multiplied by 10 divided by sine of 50 degrees, approximately 12.856. Example 2. Find the elevation of the UFO from the beginning of the section. To find the elevation of the UFO, we first find the distance from one station to the UFO, such as side A in the picture, then use right triangle relationships to find the height of the UFO H. Since the angles in the triangle add to 180 degrees, the unknown angle of the triangle must be 180 degrees minus 50 degrees minus 35 degrees equals 130 degrees. This angle is opposite the side of length 20, allowing us to set up a law of sines relationship. Sine of 130 degrees divided by 20 equals sine of 35 degrees divided by A. A equals 20 sine of 35 degrees divided by sine of 130 degrees, approximately 14.975. The distance from one station to the UFO is about 15 miles. Now that we know A, we can use the right triangle relationships to solve for H. Sine of 15 degrees equals opposite divided by hypotenuse equals H divided by 14.975. Solve for H. H equals 14.975 sine of 15 degrees, approximately 3.876. The UFO is at an altitude of 3.876 miles. In addition to solving triangles in which two angles are known, the law of sines can be used to solve for an angle when two sides and one corresponding angle are known. Example 3. In the triangle shown here, solve for the unknown sides and angles. In choosing which pair of the ratios from the law of sines to use, we always want to pick a pair where we know 3 of the 4 pieces of information in the equation. In this case, we know the angle 85 degrees and its corresponding side, so we will use that ratio. Since our only other known information is the side with length 9, we will use that side and solve for its corresponding angle. Sine of 85 degrees divided by 12 equals sine of beta divided by 9. Isolate the unknown. 9 sine of 85 degrees divided by 12 equals sine of beta. Use the inverse sign to find a first solution. Remember, when we use the inverse function, that there are 2 possible answers. Beta equals sine inverse of 9 sine of 85 degrees divided by 12, which is approximately 48.3438 degrees. By symmetry, we find the second possible solution. Beta equals 180 degrees minus 48.3438 degrees equals 131.6562 degrees. In the second case, if beta is approximately 132 degrees, then alpha would be alpha equals 180 degrees minus 85 degrees minus 132 degrees equals negative 37 degrees, which doesn't make sense, so the only possibility for this right triangle is beta equals 48.3438 degrees. With the second angle, we can now easily find the third angle since the angles must add to 180 degrees, so alpha equals 180 degrees minus 85 degrees minus 48.3438 degrees equals 46.6562 degrees. Now that we know alpha, we can proceed as in earlier examples to find the unknown side A. A equals 12 sine of 46.6562 degrees divided by sine of 85 degrees, approximately 8.7603. Notice that in the problem above, when we use law of sines to solve for an unknown angle, there can be 2 possible solutions. This is called the ambiguous case and can arise when we know 2 sides and a non-included angle. In the ambiguous case, we may find that a particular set of given information can lead to 2, 1, or no solution at all. However, when an accurate picture of the triangle or suitable context is available, we can determine which angle is desired. Example 4. Find all possible triangles if one side has length 4 opposite an angle of 50 degrees and a second side has length 10. Using the given information, we can look for the angle opposite the side of length 10. Sine of 50 degrees divided by 4 equals sine of alpha divided by 10. Sine of alpha equals 10 sine of 50 degrees divided by 4, approximately 1.915. Since the range of the sine function is negative 1, 1, it is impossible for the sine value to be 1.915. There are no triangles that can be drawn with the provided dimensions. Example 5. Find all possible triangles if one side has length 6 opposite an angle of 50 degrees and a second side has length 4. Using the given information, we can look for the angle opposite of side of length 4. Sine of 50 degrees divided by 6 equals sine of alpha divided by 4. Alpha equals 180 degrees minus 30.710 degrees equals 149.290 degrees. If we use the angle 30.710 degrees, the third angle would be 180 degrees minus 50 degrees minus 30.710 degrees equals 99.290 degrees. We can then use law of sines again to find the third side. Sine of 50 degrees divided by 6 equals sine of 99.290 degrees divided by c. Solve for c. C equals 7.730. If we use the angle alpha equals 149.290 degrees, the third angle would be 180 degrees minus 50 degrees minus 149.290 degrees equals negative 19.29 degrees, which is impossible, so the previous triangle is the only possible one.